A merchant stands in the marketplace of Miletus, calculating profit margins on olive oil shipments. The same man measures the height of Egyptian pyramids using nothing but shadows. He predicts a solar eclipse that stops a war between two armies. He proposes that everything in existence is water. He claims magnets have souls. This person existed. His name was Thales, and around 585 BCE, he asked a question nobody had asked before. Not who controls nature, but what nature actually is. Before Thales, thunder meant Zeus was angry. Earthquakes meant Poseidon struck the earth. Floods meant divine punishment. After Thales, these became phenomena with natural causes that human minds could understand. This shift from mythology to rational inquiry happened in one man's lifetime, in one Greek city on the coast of what is now Turkey. The consequences of that shift built the modern world. We know almost nothing about Thales with certainty. He left no writings. Everything we know comes from later sources, often written centuries after his death. Yet every history of philosophy and science begins with him. Aristotle called him the first philosopher. Ancient sources credited him with founding geometry, predicting eclipses, and teaching Greeks how to navigate by stars. Some stories about him are certainly legend. Some might be true. What matters is that someone, somewhere around 600 BCE, began asking questions in a fundamentally new way. The Greece of Thales' time bore little resemblance to the classical Athens of Plato and Aristotle that would emerge 2 centuries later. No Parthenon, no great philosophical schools, no democracy as we understand it. Instead, a collection of independent city-states engaged in constant trade, warfare, and cultural exchange. Miletus, where Thales lived, was among the wealthiest and most cosmopolitan, its harbor filled with ships from Egypt, Phoenicia, Babylonia, and beyond. Ideas traveled these same routes as grain and olive oil. The year 585 BCE marked a turning point, though nobody at the time could have known it. According to the historian Herodotus, Thales predicted that a solar eclipse would occur that year. When the sky darkened during a battle between the Lydians and the Medes, both armies took it as a divine sign and immediately made peace. Whether this story is accurate remains disputed. What is certain is that someone in the Greek world demonstrated that celestial events followed predictable patterns, that the heavens operated according to natural law rather than divine caprice. This was revolutionary. For thousands of years, priests had claimed exclusive access to knowledge about the cosmos, about the will of gods, about the hidden order beneath apparent chaos. Thales said anyone could understand these things through observation and reasoning. He taught in public spaces, not temples. He required no initiation into mysteries, no special revelation, no divine favor, just eyes to see, mind to think, patience to observe carefully and reason clearly. The question Thales asked seems simple. What is everything made of? His answer, that everything is water, was wrong. But asking the question changed everything. It implied that beneath the overwhelming diversity of substances and phenomena, some underlying unity might exist. It suggested that human beings could discover this unity through their own efforts. It opened the possibility that nature was comprehensible, that the universe made sense, that knowledge was achievable. 2,600 years separate us from Thales. In that time, his water theory has been replaced by atomic theory, quantum mechanics, and quantum field theory. We know things Thales couldn't have imagined, yet the fundamental approach he pioneered remains the foundation of all science and much of philosophy. Observe carefully, look for patterns, propose natural explanations, test predictions, follow evidence wherever it leads. These principles, taken for granted now, had to be invented. Someone had to be first to consistently apply them. That someone, as far as we can tell, was Thales. This is not a story of ancient wisdom lost and rediscovered. Thales was not wiser than modern scientists. He knew far less than any undergraduate physics student today. His specific theories were mostly wrong, but he established something more valuable than any particular theory. A method, an approach, a set of intellectual habits that accumulate knowledge over generations. The conversation he started continues. The questions he raised remain vital. The confidence he displayed in human capacity to understand nature still drives inquiry forward. What follows is an attempt to understand who Thales was, what he thought, why it mattered, and why it still matters. The evidence is fragmentary, the sources often unreliable, the chronology uncertain. But through the mist of 26 centuries, a figure emerges. A merchant who became a philosopher, a practical man who contemplated ultimate questions, someone who looked at the world and refused to accept that mystery was inevitable. He believed understanding was possible. He was right. That belief, more than any answer he proposed, is his gift to us. Around 585 BCE, a merchant from the Greek city of Miletus did something that had never been done before. Thales looked at the world and refused to accept the explanations everyone else took for granted. When thunder rolled across the sky, people said Zeus was angry. When crops failed, they blamed Demeter's sorrow. When earthquakes shook the ground, Poseidon was striking the earth with his trident. Thales said no. He said there must be natural reasons, causes we can find and understand without invoking gods. This sounds unremarkable now. We expect natural explanations for natural events. But in the 6th century BCE, this approach represented a complete break from thousands of years of human thinking. Before Thales, explanations came from priests who claimed special access to divine knowledge. They told stories about gods and heroes, myths that explained why things happened through the actions of supernatural beings with human emotions and desires. These stories could not be tested or questioned. You either accepted them or you didn't. Thales changed the terms. He suggested that the world operates according to principles we can discover through observation and reasoning. He didn't claim to have all the answers. He didn't say he received special revelation from any deity. He simply looked at what was in front of him and tried to make sense of it using his mind. The city of Miletus gave Thales the perfect environment for this new way of thinking. Situated on the coast of what is now Turkey, Miletus was a trading hub where Greek merchants mixed with Egyptians, Babylonians, Phoenicians, and Persians. Ideas traveled along the same routes as olive oil and grain. Thales would have encountered Egyptian geometry, Babylonian astronomy, and countless other traditions of knowledge. But he didn't just collect this information, he did something different with it. In Egypt, priests knew how to calculate the area of fields and predict when the Nile would flood. They had practical techniques that worked, but they guarded this knowledge carefully and wrapped it in religious authority. Thales took similar techniques and stripped away the mysticism. He wanted to know not just what worked, but why it worked. He wanted principles that anyone could understand and apply. This move from accepting traditional answers to demanding natural explanations marked the beginning of what we now call philosophy and science. Thales didn't use those words. He probably would have called himself simply someone who loved knowledge, but he established the template that every scientist and philosopher since has followed in some way. Observe the world, look for patterns, propose explanations based on what you can see and test. Reject appeals to authority or tradition when they conflict with evidence. The shift seems simple. It was revolutionary. For the first time, someone said that understanding the world wasn't a matter of appeasing gods or accepting what priests told you. It was a matter of thinking clearly about what you observed. This opened the possibility that anyone, not just those with special religious status, could gain real knowledge about how things work. Thales lived in a time when writing was still relatively new in Greece. Most knowledge passed orally from teacher to student, from parent to child. This meant that Thales didn't leave behind books explaining his method. We know about him through later writers who mentioned him, often in passing, when discussing the origins of philosophy. These sources tell us what Thales thought about various questions, but they give us less information about how he arrived at his conclusions. What we can piece together is that Thales consistently chose natural over supernatural explanations. When he tried to explain earthquakes, he didn't invoke angry gods. He suggested the earth floats on water, and earthquakes happen when that water becomes turbulent. This explanation turned out to be wrong, but the approach was right. He looked for a mechanism, a natural process that could account for what people observed. The same pattern appears in everything attributed to Thales. He watched the sky and noticed patterns in how celestial bodies moved. Instead of seeing these patterns as the whims of gods, he treated them as regular and predictable. This led him to successfully predict a solar eclipse, an achievement that made him famous throughout the Greek world. How he made this prediction remains unclear. He might have used Babylonian records of previous eclipses. He might have discovered a pattern himself. Either way, he demonstrated that celestial events followed rules humans could comprehend. This success mattered beyond the prediction itself. It showed that nature was intelligible. The sky wasn't chaos controlled by unpredictable divine beings. It operated according to patterns that repeated. Patterns you could study and use to anticipate what would happen next. If you could predict an eclipse, what else might you predict? What other aspects of the world might follow discoverable rules? Thales applied the same thinking to practical problems. Merchants needed to measure land accurately. Builders needed to know if their structures would stand. Sailors needed to navigate by the stars. These weren't abstract philosophical questions. They were real challenges that affected people's lives and livelihoods. Thales showed that careful observation and clear thinking could solve these problems better than traditional methods based on ritual or guesswork. The question that drove Thales was simple but profound. Why do things happen the way they do? not who makes them happen, not what story explains them, why, what causes what principles govern events. This shift from who to why, from story to principle, from myth to nature, created the foundation for everything that came after in Western thought. People before Thales were not stupid. They were not incapable of observation or reasoning, but they lived in cultures where the default explanation for any mysterious phenomenon involved the actions of gods or spirits. Thales gave permission to look for different kinds of answers. He demonstrated that you could explain the world without reference to supernatural intervention, and that doing so often led to better, more useful understanding. The world Thales described was not empty of divinity. He made statements suggesting that everything contained something divine, but his divinity wasn't the gods of traditional religion who answered prayers and punished wrongdoing. It was something else, something tied to the nature of things themselves, rather than to beings who stood outside nature and manipulated it. This approach spread. Other thinkers in Miletus and beyond began asking similar questions and proposing natural explanations. They disagreed with each other about the answers, but they agreed on the method. They would observe, reason, and debate rather than accept traditional stories unchallenged. This community of inquiry, this willingness to question and argue and revise ideas based on evidence and reasoning, became the heart of the intellectual tradition Thales initiated. Walking through Miletus in Thales' time, you would have seen a bustling port city with ships from across the Mediterranean. You would have heard a dozen languages, seen temples to various gods, watched merchants haggling over prices. In this cosmopolitan environment, Thales saw an opportunity. If people from different cultures could trade and communicate despite their differences, perhaps there were also universal principles that transcended any particular tradition. Perhaps truth was not relative to your city or your gods, but something more fundamental. This universalism became central to the tradition Thales started. Philosophy and science claimed to seek truths that hold everywhere for everyone, regardless of culture or religion. This was an audacious claim in a world divided into competing city-states with different gods and customs. Thales implied that beneath all the surface differences, nature operated the same way everywhere. The same forces that caused eclipses in Miletus caused them in Egypt. The same geometry that measured fields in Babylonia worked in Greece. Thales made a claim that seems strange at first. He said everything is water. Not that everything contains water or that water is important. Everything is water, fundamentally. All the diverse things you see around you, the rocks and metals, the plants and animals, the air you breathe and the fire that burns, all of it is water in different forms. This sounds bizarre until you consider what Thales was trying to do. He was searching for unity beneath diversity. The world presents us with an overwhelming variety of substances and phenomena. Thales wanted to know if this variety might reduce to something simpler, some single underlying reality that takes different forms. Why water specifically? Thales had reasons. Water exists in 3 states that anyone can observe. It flows as liquid. It freezes into solid ice. It evaporates into invisible vapor. Here was one substance that could be hard or soft, visible or invisible depending on conditions. If water could change so dramatically while remaining fundamentally the same substance, perhaps all apparent differences between things were similar transformations of a single underlying material. Thales also noticed that water seems essential to life. Seeds won't sprout without moisture. Animals die without water to drink. Even the driest wood contains some moisture, which you can see when green wood hisses and steams in fire. Everywhere Thales looked, he saw water involved in growth, change, and vitality. This suggested water might be more fundamental than other substances. The claim wasn't metaphorical. Thales wasn't saying water represents something or symbolizes some spiritual principle. He meant it literally. Everything is actually water, transformed and modified in ways that make it appear different. A rock is water that has somehow solidified. Air is water that has become extremely fine and dispersed. Fire might be water in an excited, energetic state. This theory was wrong. We now know matter consists of atoms of many different elements, not transformations of a single substance. But the error doesn't diminish the importance of what Thales did. He proposed a testable claim about the fundamental nature of reality. He looked for the simplest possible explanation that could account for what he observed. He tried to unify apparently unrelated phenomena under a single principle. This approach, seeking the simplest explanation that fits the facts, became central to scientific thinking. Don't multiply entities beyond necessity. If you can explain everything with one fundamental substance, don't propose 10. Thales applied this principle consistently. The water theory also reveals something about how Thales thought. He wasn't content with knowing how to work with different materials. He wanted to know what they were, in some deeper sense. A A craftsman knows that iron behaves differently from wood, and that's enough for making things. Thales wanted to know if iron and wood might be the same thing underneath their different behaviors. This question had no practical value. It wouldn't help you build better ships or forge better tools. Thales asked it anyway, because understanding mattered to him independently of utility. Other thinkers before Thales had proposed origin stories. Most cultures have creation myths explaining where the world came from. Usually these involve gods creating the world from chaos, or emerging from cosmic eggs, or defeating primordial monsters. Thales stripped all that away. No gods, no cosmic battles, no supernatural events, just water, changing form according to natural processes. This naturalistic approach opened new questions. If everything is water, what makes water change into different forms? What drives these transformations? Thales didn't provide detailed answers, but he established that these were the right questions to ask. Look for natural processes, not divine intervention. Look for mechanisms, not myths. The water hypothesis also implied something radical about permanence and change. If a rock is really water in solid form, then nothing stays fundamentally the same. Everything is in flux, potentially transforming into something else. Yet despite all this change, something persists. The water itself remains, even as it takes different shapes and states. Thales grappled with a problem that would occupy philosophers for centuries. How can things change yet remain somehow identical to themselves? Consider a piece of ice melting into liquid water, then evaporating into steam. At each stage, it seems like a different substance with different properties. Ice is hard and you can stand on it. Liquid water flows and you can drink it. Steam is invisible and rises into the air. Yet we recognize all three as water. Thales extended this recognition to everything. Perhaps the rock and the river and the cloud are as different as ice and liquid and steam, but just as those are all water, maybe everything is transformations of some single substance. He chose water, but the specific substance mattered less than the approach. Thales claimed that diversity emerges from unity, that complexity arises from simplicity, that the many are ultimately one. This claim has echoed through Western thought ever since. Scientists still search for unified theories that explain all forces and particles. Philosophers still debate whether reality is fundamentally one thing or many things. Thales asked these questions first. The water theory also reflected Thales' environment. Miletus stood on the coast, surrounded by water. The sea brought trade and prosperity. Rivers provided fresh water for drinking and irrigation. Rain determined whether crops flourished or failed. Water was life. In a landscape where water's presence or absence made the difference between abundance and famine, choosing water as the fundamental substance made intuitive sense. But Thales didn't just reflect his environment, he thought about it. He noticed that water moves from sea to sky to land in a continuous cycle. Rain falls, rivers flow to the ocean, the sun evaporates seawater which forms clouds which produce more rain. This cycle suggested that water was somehow prior to other substances, that it drove the processes that shaped the world. Thales also observed that land itself seems to float on water. Dig down far enough anywhere and you hit groundwater. Islands rise from the sea. The Mediterranean coastline where Thales lived showed him land and water in constant interaction. Shorelines shifted with storms and tides. Rivers deposited silt that created new land. The boundary between earth and water was fluid, not fixed. This observation supported his idea that earth might be a form of water, condensed and hardened but not fundamentally different. The theory had explanatory power beyond what we might initially recognize. It provided a framework for understanding how things come to be and pass away. When something dies or decays, where does it go? It returns to water, Thales might say. When something new grows or forms, where does it come from? From water, taking on a new shape. Birth and death, growth and decay, all became transformations of the underlying substance. This framework didn't require any breaks in natural law. You didn't need gods intervening to create things from nothing or to make them disappear into void. Everything moved in a continuous process of transformation. Water to plant, plant to animal, animal back to earth, earth back to water. The circle closed. Nothing was truly created or destroyed, only changed. Thales never explained exactly how these transformations worked. He didn't have the conceptual tools to talk about chemical reactions or phase transitions or molecular structure. He simply observed that change happens and proposed that beneath all change lies something unchanging. This insight, that there might be conservation laws governing transformation, anticipated modern physics by more than 2,000 years. The water theory also addressed a puzzle that troubled Greek thinkers. How can something come from nothing? If the world had a beginning, what existed before? If nothing existed, how did something arise? Thales sidestepped this problem. Water always existed. It never came from nothing. All the apparent variety in the world emerged through reorganization of what was already there. The question shifted from creation to transformation. This move had profound implications. It suggested the universe might be eternal, with no beginning and no end. Forms come and go, but the substance persists forever. This conflicted with traditional religious views that described gods creating the world at some specific moment in the past. Thales offered an alternative, a world that always was and always will be, changing constantly but never beginning or ending. The theory also implied something about knowledge. If everything reduces to transformations of water, then understanding water means understanding everything. The diversity that seems so overwhelming becomes manageable. You don't need separate explanations for rocks and clouds and blood and bone. You need one explanation that accounts for how water takes different forms. This reduction promised to make knowledge achievable. The world was comprehensible because it was, at bottom, simple. Thales didn't convince everyone. His student Anaximander rejected the water theory and proposed that the fundamental substance was something else, something undefined and unlimited. Other thinkers proposed air or fire or combinations of elements, but they all accepted Thales' basic approach. Look for natural substances and processes. Reduce complexity to something simpler. Seek unity beneath diversity. The water hypothesis also raised questions about human beings. If everything is water, what are we? Thales would say we're water arranged in a particular pattern, a temporary organization that maintains itself for a while then disperses. This view challenged the idea that humans have some special status, some essence different from rocks and trees. We're made of the same stuff as everything else, just arranged differently. This naturalistic view of humanity was as radical as the naturalistic view of the cosmos. Traditional thought placed humans in a unique category, made in the image of gods or possessing immortal souls. Thales suggested we're part of nature, governed by the same principles as everything else. This didn't make human life meaningless, but it did remove humans from any privileged position in the cosmic order. Thales made his living trading goods across the Mediterranean. He wasn't born into wealth or aristocracy. He worked, calculated, took risks, succeeded, and failed like any merchant. This practical background shaped everything about how he approached knowledge. Merchants live by observation and prediction. You watch the weather to know when to sail. You track which goods are scarce where, anticipating what will fetch high prices in different ports. You calculate distances, costs, profit margins. A merchant who can't observe accurately and predict reliably doesn't stay in business long. Thales brought this same mentality to questions about nature. The eclipse prediction made Thales famous throughout the Greek world. According to the historian Herodotus, Thales predicted that an eclipse would occur during a particular year, and when it happened, it interrupted a battle between the Lydians and the Medes. The armies took the darkening sun as a divine sign and made peace immediately. Whether this story is accurate in all details is unclear, but ancient sources consistently credit Thales with successfully predicting an eclipse. How did he do it? We don't know exactly. Thales left no written explanation of his methods. The Babylonians had been keeping careful records of eclipses for centuries and had noticed patterns in when they occurred. Thales might have learned about these records during his travels. He might have used Babylonian data to calculate when the next eclipse would be visible from Greece, or he might have discovered the patterns himself through patient observation of the sky over many years. What matters is that he did it using natural principles, not religious ritual. Priests in various cultures claimed they could predict or even cause eclipses through proper ceremonies and sacrifices. Thales showed that eclipses follow regular patterns that anyone can study and use to make predictions. The sun doesn't darken because a god is angry. It darkens because the moon passes between Earth and sun at predictable intervals. This demonstration had enormous impact. It proved that celestial events, which seemed most obviously controlled by gods, actually follow natural laws. If you could predict an eclipse, what else might you predict? The heavens weren't the realm of divine caprice. They were orderly, regular, knowable. The prediction also established Thales' reputation as someone whose knowledge worked. He didn't just speculate about nature. He made specific claims that could be tested, and when tested, they proved accurate. This gave his other ideas credibility they might not otherwise have had. If Thales could predict eclipses, maybe his ideas about water and earthquakes deserve serious consideration too. But Thales didn't just predict eclipses. He applied his thinking to concrete problems merchants and builders faced every day. One story tells how Thales helped merchants cross a river with their goods. The river was too deep to ford with loaded pack animals. Thales suggested digging a channel to divert part of the river's flow, lowering the water level enough to cross safely. Whether this specific incident happened is less important than what it reveals about how Thales was remembered, as someone who solved practical problems through understanding nature. Another story describes Thales measuring the height of pyramids in Egypt using shadows. He waited until the time of day when his own shadow was exactly as long as he was tall, then measured the pyramid's shadow. At that moment, the pyramid's shadow equaled its height. This technique didn't require climbing the pyramid or any complex equipment. It just required understanding that shadows and objects maintain consistent proportions at any given time of day. This method shows Thales thinking like a geometer. He recognized that similar triangles have proportional sides. When the sun is at a certain angle, every vertical object casts a shadow in the same proportion to its height. This insight let him measure things that couldn't be measured directly. The same principle works for measuring the distance to ships at sea or the height of mountains. These practical achievements matter because they show philosophy emerging from engagement with the world, not retreat from it. Thales didn't sit in isolation contemplating abstract questions. He traveled, traded, observed, calculated, solved problems. His philosophical ideas grew from this active involvement with nature and commerce. The story about monopolizing olive presses makes this point vividly. According to Aristotle, people criticized philosophers as useless, impractical dreamers. Thales decided to prove them wrong. Using his knowledge of weather patterns, he predicted that the next olive harvest would be unusually large. During winter, when nobody wanted olive presses, he quietly rented all the presses in Miletus and the surrounding area for very little money. When harvest came and his prediction proved correct, olive growers desperately needed presses. Thales controlled them all and could charge whatever he wanted. He made a fortune, demonstrating that philosophers could succeed in business if they chose to, then returned to his studies. Whether this happened exactly as told is uncertain. The story might be legendary, but it illustrates how Greeks thought about Thales as someone who combined abstract thinking with practical skill, who could predict natural phenomena and profit from those predictions, who proved that understanding nature had real value beyond mere curiosity. This combination of theory and practice characterized the Milesian approach to knowledge. These weren't scholars shut away in libraries. They were active participants in a commercial city, and they brought the merchants' emphasis on what works to their study of nature. An idea that couldn't be tested or applied remained suspect. An idea that led to accurate predictions and useful techniques gained credibility. Thales also contributed to navigation. Sailors had long used the stars to orient themselves at sea, but their methods were rough and traditional. Thales reportedly taught Greek sailors to navigate using the Little Bear constellation, which included the pole star. Phoenician sailors already used this technique, but Greek sailors relied on different stars. By adopting the Phoenician method, Greek sailors could navigate more accurately, especially over long distances where small errors in direction compound into large deviations. This wasn't revolutionary astronomy. Thales didn't discover new stars or propose new theories about celestial motion. He simply recognized that one navigation method worked better than another and spread that knowledge. But this practical contribution saved lives and improved commerce. Ships that could navigate more accurately reached their destinations more reliably, avoiding storms and rocks and hostile coastlines. Thales' work in geometry also had practical applications. He proved, or at least was credited with proving, several geometric theorems that builders and surveyors used. One theorem states that a circle is bisected by its diameter. Another states that the angles at the base of an isosceles triangle are equal. These might seem obvious, but proving them rigorously was important. It established that geometric facts weren't just rules of thumb that usually worked. They were necessary truths that always held. This distinction between approximate rules and rigorous proofs became central to Greek mathematics. Egyptian surveyors knew that a triangle with sides of length 3, 4, and 5 units forms a right angle. They used this knowledge to lay out buildings with square corners, but they didn't prove why this worked or investigate whether other combinations of lengths also formed right angles. Greek geometers, following the path Thales opened, wanted proofs and general principles. The practical knowledge Thales accumulated came from many sources. He traveled to Egypt and probably to Babylonia. He talked with merchants, sailors, builders, priests, astronomers from various cultures. He collected techniques and observations from everywhere he went. But he didn't just collect. He organized, compared, questioned, tested. He looked for underlying principles that could explain why these various techniques worked. This approach made Thales more than an accomplished tradesman. It made him someone who sought understanding for its own sake. while recognizing that understanding often led to practical benefits. He saw no conflict between pursuing knowledge and making a living, between understanding nature and profiting from that understanding. The same careful observation that revealed natural patterns could identify business opportunities. Thales proved that philosophers didn't have to be impractical dreamers disconnected from ordinary life. You could think deeply about fundamental questions while also solving concrete problems. You could seek truth while also seeking profit. You could be a successful merchant and a groundbreaking thinker simultaneously. These roles reinforced rather than contradicted each other. This integration of thought and action influenced all subsequent Greek philosophy. Philosophers might disagree about what questions mattered most or what methods worked best, but most accepted that ideas should connect to reality in testable ways. Abstract speculation that never touched the actual world remained suspect. Thales established that good thinking produced results you could demonstrate. Thales made a statement that seems to contradict everything else about his approach. He said all things are full of gods. After rejecting divine explanations for natural phenomena, after proposing that everything is water following natural laws, he apparently reintroduced divinity everywhere. This looks like inconsistency until you understand what Thales meant by gods. He wasn't talking about Zeus throwing lightning bolts or Poseidon causing earthquakes. Thales had rejected those kinds of explanations. When he said everything is full of gods, he meant something different. He was describing an inner principle of activity, a power within things themselves that makes them behave as they do. Consider a piece of magnetite, a naturally magnetic rock. Ancient Greeks called this material lodestone. Thales observed that lodestone attracts iron. It moves iron objects without being moved itself. This seemed remarkable. How could one rock make another piece of metal move without touching it? Traditional explanation, a god makes it happen. Thales' explanation, the stone itself has a kind of soul or life that allows it to cause motion. This explanation might not seem much better than invoking gods, but there's a crucial difference. Thales located the cause of motion within the stone itself, not in some external supernatural being. The lodestone doesn't move iron because Hephaestus or some other god intervenes. It moves iron because of its own nature, its own inherent properties. The stone is full of divine power in the sense that it contains within itself the principle of its activity. Thales extended this idea to everything. All things possess an inner principle that makes them what they are and causes them to behave as they do. Fire burns not because a fire god makes it burn, but because fire itself contains the principle of burning. Water flows not because a river god directs it, but because flowing is part of water's nature. This divine element isn't separate from nature. It is nature, understood as self-moving and self-directing. This view had radical implications. It meant the world didn't need gods outside it pulling strings and making things happen. The world contained its own principles of motion and change. Nature was autonomous, running according to its own internal logic rather than external commands. This made the universe fundamentally intelligible. To understand why things happen, you study the things themselves, not the supposed intentions of gods. The idea also challenged the boundary between living and non-living. Traditional thought drew a sharp line between things with souls, which could move themselves, and things without souls, which could only be moved by external forces. Animals and humans have souls and move themselves. Rocks and water don't have souls and only move when something pushes them. Thales blurred this distinction. If lodestone can cause motion through its own nature, maybe everything has some degree of life or soul, some internal principle of activity. This doesn't mean Thales thought rocks were conscious or had feelings. Soul here means something more like a principle of self-motion or inherent power. Water doesn't think or feel, but it does have a tendency to flow downward, to freeze when cold, to evaporate when heated. These aren't behaviors imposed from outside. They're expressions of what water is. Modern readers might see this as primitive animism, projecting life onto lifeless matter. But Thales was moving in the opposite direction from animism. Traditional animism explains natural phenomena by attributing human-like intentions to nature. The river floods because it's angry. The sun shines because it's benevolent. Thales removed these anthropomorphic projections. Nature doesn't have human emotions or intentions. It has its own properties and principles. Calling these principles divine preserved continuity with traditional religious language while transforming what that language meant. Instead of gods as human-like beings who created and controlled nature from outside, divinity became the inner creative power of nature itself. This move anticipated later developments in both philosophy and theology. Philosophers would debate whether the universe needs an external creator or contains its own principle of order. Theologians would argue about whether God is separate from creation or somehow present within it. Thales didn't develop these ideas in detail. Later thinkers took up the questions he opened. But his basic insight that things have inherent natures that explain their behavior became foundational. When Aristotle analyzed causation centuries later, he distinguished between external causes that push things around and internal causes that express a thing's own nature. This distinction goes back to Thales' observation that lodestone moves iron through its own power. The statement that all things are full of gods also suggests that Thales saw the world as thoroughly unified. Everything participates in the same underlying reality. The divine isn't concentrated in special places like temples or present only at special times during rituals. It pervades everything everywhere always. This implied a kind of equality among things. A rock on the ground contains the same fundamental reality as the stars in the sky. Both are water in different forms, both are full of gods in the sense of possessing inherent natures. This view made the world more accessible to understanding. If divinity means transcendent beings utterly different from nature, then understanding nature tells you nothing about the divine. But if divinity means the inherent power and nature of things, then understanding nature is understanding the divine. Science and theology converge. Studying how things work becomes a form of studying the sacred. Whether Thales used the word gods to describe this because he genuinely saw it as divine or because he wanted to make his ideas less shocking to traditional believers is unclear. Probably both motives played a role. Thales was proposing a radical reinterpretation of divinity, not an outright rejection of it. This made his ideas easier to accept while still transforming how people thought about gods and nature. The magnetic rock example reveals Thales' method. He paid attention to phenomena that seemed puzzling or exceptional. Most rocks don't attract iron. Why does lodestone? This question led him to think about what makes different things behave differently. If everything is water, why does water take so many forms with such different properties? Because the divine element within things shapes how they manifest. This wasn't a very precise answer, but it pointed toward the right kind of answer. Look for inherent properties, not external interventions. Thales also reportedly said that the magnet has soul because it moves iron. This statement links soul directly to the capacity to cause motion. Soul isn't something added to matter, it's the power within matter to affect other matter. This materialist understanding of soul contrasted sharply with views that saw soul as immaterial and separable from body. For Thales, soul and matter weren't separate categories. Soul was matter's own active power. This view influenced later Greek thought about psychology and physics. If soul is the principle of motion, then understanding motion means understanding soul. Conversely, understanding soul requires understanding the physical processes through which things move and change. Mind and matter, psychology and physics couldn't be completely separated. Both involved studying the same underlying reality from different angles. The claim that everything is full of gods also addressed the question of order. Why does nature show patterns and regularity? Why do the same causes produce the same effects? Traditional answer, gods impose order on chaos. Thales' answer, order emerges from the inherent natures of things. Water behaves consistently because being water means having certain properties. These properties aren't arbitrary commands from outside. They're what water is. This made natural law possible as a concept. Laws of nature aren't rules that nature follows because some legislator decreed them. They're descriptions of how things naturally behave given what they are. Water flows downward not because a rule requires it, but because flowing downward expresses water's nature. Fire burns because burning is what fire does. The regularity we observe in nature reflects the consistency of things' inherent properties. Thales didn't use the phrase laws of nature. That language came later. But he laid the groundwork for it by suggesting that things behave consistently because of what they are, not because external forces constantly intervene to make them behave that way. Nature is self-regulating, containing within itself the principles of its own operation. Thales trusted his senses. This might seem unremarkable, but it represented a specific choice about how to gain knowledge. Many traditions taught that true knowledge comes from revelation, from priests who communicate with gods, from ancient texts, from inner mystical experiences. Thales said no. Look at the world. Pay attention to what you can see, hear, touch. That's where knowledge starts. This empirical approach had limits Thales recognized. You can't see everything. The senses make mistakes. What looks like a straight stick becomes bent when you put it in water. But these problems didn't make Thales abandon observation. Instead, he became more careful about how to observe and more sophisticated about interpreting what he saw. The bent stick in water is illusion, but it's regular, predictable illusion. Every straight object looks bent when partially submerged. This consistency suggests something real is happening, even if it's not what it first appears. Thales didn't have the concept of refraction, but he could recognize that water affects how we see things passing through it. Careful observation reveals not just that the senses sometimes deceive, but also the patterns in how they deceive. Thales' measurement of the pyramids shows sophisticated observation in action. He didn't just look at pyramids and guess their height. He set up conditions where shadows would give him the information he needed. He chose a specific time of day when the proportions worked in his favor. He measured carefully. This wasn't passive reception of sense data. It was active engagement with the world, arranging circumstances to reveal what he wanted to know. The same active approach appears in Thales' geometric work. He proved that when two straight lines intersect, the opposite angles are equal. You can't prove this just by looking. You can draw intersecting lines and measure the angles, and they'll be equal. But measurement might be slightly off, and checking a few cases doesn't prove the angles are always equal. Thales looked for logical necessity, not just empirical regularity. This combination of observation and reasoning became central to scientific method. You observe to gather data and identify patterns. You reason to understand why patterns hold and to predict cases you haven't observed yet. Neither observation nor reasoning alone suffices. You need both working together. Thales also recognized that some things can't be observed directly, but can be inferred from what you do observe. You can't see the whole Earth, but you can observe that ships disappear hull first over the horizon, suggesting the Earth's surface curves. You can't see the moon blocking the sun during a solar eclipse, but you can observe the shadow moving across the Earth and infer what must be causing it. This willingness to go beyond direct observation while remaining tethered to it marked Thales' approach. He made claims about the fundamental nature of reality, about water being the basis of all things, that couldn't be verified through simple observation. But these claims connected to things he could observe. Water's transformations, its presence in living things, its cycles through sea and sky and land, all observable phenomena that suggested water's fundamental role. The practice of careful observation required patience. You couldn't understand celestial patterns by watching the sky for one night. You needed to track movements over months and years. Thales or someone before him had to keep records, noting where stars appeared at different times of year, when eclipses occurred, how planets moved against the background of stars. This long-term systematic observation differed from casual noticing. It also required trust that nature was consistent enough to make observation worthwhile. If the world operated capriciously, if stars moved differently each night according to divine whim, observation would teach you nothing. Each event would be unique and unpredictable. Thales' commitment to observation implied faith that nature follows regular patterns that repeated observation can reveal. This faith proved justified. The patterns were there, celestial motions repeated in cycles, geometric relationships held consistently, materials behaved the same way under the same conditions. Nature was intelligible to patient, careful observers. This didn't mean everything was obvious or easy to understand. It meant that effort spent observing and thinking about observations paid off in increased understanding. Thales also understood that observation could correct traditional beliefs. People said the Earth was flat and stationary. Observation of ships on the horizon suggested otherwise. People said celestial events were unpredictable acts of gods. Observation revealed patterns that enabled prediction. People said different materials were fundamentally different substances. Observation of transformation suggested underlying unity. This critical function of observation, its power to challenge accepted ideas, made it threatening to those who based authority on tradition or revelation. If observation shows that traditional teachings are wrong, what happens to the authorities who taught them? Thales didn't emphasize this conflict, but it was implicit in his method. Trust what you can verify through observation and reasoning more than what authorities tell you. The democratic implications were significant. Observation doesn't require special status or divine favor. Anyone with functional senses and a thinking mind can observe the world and draw conclusions. Thales didn't claim secret knowledge available only to initiates. He pointed to things everyone could see and asked them to think about what those things meant. This opened philosophy to anyone willing to make the effort. Thales' geometric proofs exemplified observation transformed by thought. You start by observing geometric figures, drawing triangles and circles, measuring angles and lengths. You notice patterns. All circles seem to be bisected by their diameters. The angles at the base of isosceles triangles seem equal. But observation alone can't tell you these relationships must hold. You need reasoning to prove necessity. The proof itself isn't just logical manipulation. It requires insight, seeing relationships that aren't obvious from mere observation. When Thales proved that a triangle inscribed in a semicircle is always a right triangle, he saw a connection between circles and right angles that observation alone wouldn't reveal. But the proof could be tested through observation. Draw the figures, measure the angles, confirm the reasoning. This interplay between observation and reasoning produced a new kind of knowledge, more certain than mere observation but more connected to reality than pure logic. You couldn't just think your way to geometric truths while ignoring figures and measurements, but you couldn't just measure without reasoning about what the measurements meant. The two capacities worked together. Thales applied the same approach to natural phenomena. He observed earthquakes and floods, droughts and storms. He looked for patterns in when and where these events occurred. He proposed explanations based on what he could observe about earth, water, and their interactions. His explanations could be tested against further observation. If earthquakes always occurred near water, that supported his theory that Earth floats on water. If earthquakes happened equally often everywhere, that would undermine it. This testability distinguished Thales' explanations from mythological ones. If you say Poseidon causes earthquakes, how do you test that? You can't observe Poseidon. You can't predict when he'll be angry. The explanation doesn't connect to anything you can check. But if you say Earth floats on water and earthquakes are disturbances in that water, you can look for evidence. Do earthquakes cluster in certain regions? Is there a relationship between earthquakes and tides or other water movements? The explanation generates questions that observation can address. Thales didn't have the tools to fully test his earthquake theory. Ancient Greeks couldn't drill deep into the earth or measure seismic waves. But he established the principle that natural explanations should connect to observable phenomena in ways that let you evaluate whether they're correct. This principle guided all subsequent science. The power of observation also meant accepting unwelcome conclusions. If observation consistently contradicts your ideas, you need to revise your ideas, not deny what you observe. Thales demonstrated this intellectual honesty. When evidence suggested the earth wasn't flat, he accepted that, even though it contradicted common sense and traditional belief. When observations showed that celestial events followed patterns, he built theories around those patterns rather than insisting divine caprice explained everything. This willingness to follow evidence wherever it led, even when it contradicted tradition or intuition, became a hallmark of scientific thinking. You don't get to pick and choose which observations to accept based on whether they fit your preferences. If observation reliably shows something, that's reality, and your job is to understand it, not wish it away. Thales also recognized that observation could be enhanced by instruments and techniques. The shadow method for measuring height was an early example. You couldn't measure a pyramid's height by putting a ruler against it, but you could use shadows to convert the problem into something measurable. Later thinkers developed more sophisticated instruments and techniques, but the principle came from Thales. Find ways to make the unobservable observable, the unmeasurable measurable. The world presents itself as overwhelming diversity, thousands of different substances, countless types of events, endless variety in shapes and sizes and properties. Faced with this chaos, Thales asked whether underlying order might explain the surface confusion. Could all this diversity reduce to something simpler? This question drove his claim that everything is water. If true, it would mean the apparent chaos of countless different substances was really the order of one substance taking many forms. The problem of understanding everything would become the more manageable problem of understanding water and how it transforms. But Thales sought order in more than just material substance. He looked for patterns in how events unfold, regularities that let you predict what will happen next. The eclipse prediction demonstrated this kind of order. Celestial motions that seem random and unpredictable actually follow patterns. Once you recognize the patterns, you can anticipate future events. This faith in underlying order wasn't self-evident. The world could have been fundamentally chaotic, with events occurring randomly and unpredictably. Nothing required that nature follow patterns. Yet Thales assumed it did and set about finding them. This assumption became a cornerstone of science. Nature is orderly. Our job is to discover that order. The assumption proved remarkably fruitful. Everywhere investigators looked, they found patterns and regularities. Some remained hidden for centuries, requiring sophisticated instruments and mathematics to reveal. But they were there. The universe turned out to be far more orderly than anyone might have guessed from casual observation. Thales' faith in order was vindicated repeatedly. What made Thales think order existed beneath apparent chaos? Partly observation. Water does transform between ice, liquid, and vapor in regular ways. Celestial bodies do move in repeating patterns. Geometric relationships do hold consistently. But partly it was a choice, a decision to look for order rather than accept chaos. This choice wasn't arbitrary. Order made the world comprehensible. Chaos left everything mysterious and unknowable. The search for order also involved finding the right level of description. At the most detailed level, every moment is unique. No two leaves are identical. No two waves break exactly the same way. If you focus on unique details, you'll never find patterns. Thales looked past individual differences to common features. All leaves grow on plants. All waves involve water moving. At this more abstract level, order emerges. This abstraction, this looking past specific details to general patterns, became essential to scientific thinking. You can't predict exactly which leaf will fall next from a tree, but you can predict that leaves fall in autumn when temperatures drop. You can't predict the exact shape of the next wave, but you can predict that waves move toward shore when wind blows from the sea. Finding order means finding the right level of abstraction where patterns become visible. Thales' geometry exemplified this approach. An actual drawn triangle is never perfectly triangular. The lines have width, the angles aren't exactly precise, the whole figure exists in a specific place at a specific time. But Thales proved things about triangles in general, about the abstract idea of triangle that all actual triangles approximate. This move to abstraction let him find order, eternal truths about triangles that remained constant despite the imperfection of any particular example. The same pattern appeared in his natural philosophy. Actual samples of water differ. Seawater tastes salty. River water tastes fresh. Water from different sources might be muddy or clear, cold or warm, still or flowing. But underneath these differences, it's all water. Thales looked past the variations to the common substance. This abstraction from particular cases to general principles became fundamental to scientific method. The search for order also meant looking for causes. Why do things happen as they do? Random chaos has no causes, just arbitrary events. But if order exists, effects must follow from causes according to regular principles. Thales consistently sought causes. Earthquakes have causes in movements of water. Eclipses have causes in movements of celestial bodies. Nothing happens without a cause, and causes operate consistently. This principle of causation, that every effect has a cause and similar causes produce similar effects, made prediction possible. If you understand what causes something, you can predict when it will happen again. If you know what causes eclipses, you can predict future eclipses. If you know what causes earthquakes, you can perhaps predict or prevent them. Understanding causes meant gaining power over nature. Thales didn't claim to know all causes. Many phenomena remained mysterious, but he assumed causes existed even for things he couldn't explain. This assumption drove investigation. If you believe events are random, there's no point studying them. But if you believe they have discoverable causes, studying them makes sense. You might not succeed immediately, but eventual success becomes possible. The order Thales sought wasn't imposed from outside. He didn't imagine gods creating order out of chaos, organizing matter according to plans. Order arose from the inherent natures of things. Water behaves the way it does because of what water is. This means order is accessible through studying nature itself, not through revelation about divine intentions. This naturalistic understanding of order had profound implications. It meant you didn't need to consult priests or sacred texts to understand why things happen. You needed to observe nature and think carefully about what you observed. Authority shifted from religious specialists to careful thinkers who based claims on evidence and reasoning. The geometric order Thales studied was particularly striking. Geometric truths hold necessarily. A circle must be bisected by its diameter. This isn't something that happens to be true but might have been otherwise. It couldn't be otherwise. This necessity suggested that at least some aspects of order in nature were absolute, unchangeable, eternal. This discovery of necessary truths, accessible through reasoning, excited Greek thinkers enormously. If geometry could yield certain knowledge, perhaps other domains could too. Perhaps beneath the flux and change of the material world lay eternal truths about how things must be. This hope drove much of Greek philosophy and science. Thales also recognized patterns of transformation. Things change from one form to another, but the changes follow regular sequences. Water freezes when cooled, evaporates when heated. Seeds sprout in spring, plants die in winter. Birth, growth, death, decay follow predictable patterns. These cycles suggested order in the temporal dimension, not just the spatial. The combination of material unity, everything being water, and regular patterns of transformation created a vision of the world as fundamentally orderly and comprehensible. This vision contrasted sharply with seeing the world as chaos barely controlled by capricious gods. Thales offered an alternative, a world that made sense, that followed principles humans could discover and understand. This vision made ethics possible too, though Thales didn't develop ethical ideas explicitly. If the world is orderly, if causes produce effects consistently, then human actions have predictable consequences. You can figure out how to live well by understanding how actions lead to outcomes. Ethics becomes a kind of natural science, discovering the causes of human flourishing. Later Greek thinkers pursued this connection between cosmic order and human order. If the universe follows rational principles, shouldn't human society too? If nature shows harmony and balance, shouldn't individuals and cities seek the same? Thales opened these questions without answering them, but his vision of an orderly cosmos suggested that human life might likewise be orderly and comprehensible. The mathematical order Thales found was especially important. Numbers and geometric relationships seemed to describe nature accurately. The proportions between shadows and heights that let him measure pyramids weren't arbitrary. They reflected real mathematical relationships in how light and objects interact. This suggested mathematics might be the key to understanding nature, a language that described how things actually work. This idea that nature is mathematical became central to science. Galileo later said the book of nature is written in the language of mathematics. Newton showed that planetary motions follow mathematical laws. Modern physics expresses fundamental principles in mathematical equations. Thales took the first steps down this path by recognizing that geometric relationships describe real features of the world. Thales earned the title of first scientist not because he made the most discoveries or had all the right answers. Most of his specific theories proved wrong. The Earth doesn't float on water. Not everything is water. Earthquakes don't result from turbulence in cosmic oceans. But Thales established the approach that defines science: natural explanations, testable claims, systematic observation, logical reasoning. Science requires that explanations refer only to natural causes, things that operate through physical processes we can study. No miracles, no supernatural interventions, no gods reaching in from outside to make things happen. Thales consistently applied this principle. Every phenomenon he tried to explain, he explained through natural mechanisms. Water, not gods. Physical processes, not divine will. This naturalism wasn't atheism. Thales said everything is full of gods, but his gods were nature's own inherent powers, not beings who manipulated nature from outside. This redefinition of divinity made science possible. If gods constantly intervene in natural processes, science becomes impossible. You can't discover laws of nature if nature's operations depend on unpredictable divine whims, but if nature operates through its own principles, those principles can be discovered. Science also requires testability. A scientific claim must connect to observable consequences that let you check whether it's correct. Thales' eclipse prediction demonstrated this. He made a specific claim that could be verified or falsified. When the eclipse occurred as predicted, his claim gained credibility. If it hadn't occurred, his claim would have been refuted. Not all of Thales' ideas were equally testable with ancient technology. His claim that everything is water couldn't be easily verified or falsified. Ancient Greeks lacked the tools to break matter down to its components. But the claim at least had empirical content. It said something about the world that made a difference to what you should observe. If everything is water, transformations between apparently different substances should be possible. You should be able to find connections between water and other materials. The commitment to testability distinguished Thales from mythological thinkers. Myths make claims that can't be tested. How would you verify that Zeus throws lightning bolts? You can't observe Zeus. You can't experiment with divine thunderbolts. The claim explains lightning by reference to something even more mysterious than lightning itself. Thales explained phenomena by reference to things you could observe and study: water, magnets, shadows, stars. Science also requires systematic observation. Casual, random noticing isn't enough. You need to observe carefully, repeatedly, under different conditions. You need to keep records, track patterns over time, compare different cases. Thales observed eclipses systematically enough to predict one. He observed water systematically enough to notice its transformations and cycles. This methodical approach separated him from people who just passively received impressions. Reasoning plays a central role in science too. Observation provides data, but reasoning interprets it, finds patterns, proposes explanations, makes predictions. Thales' geometric proofs showed rigorous reasoning in action. He started with observations but went beyond them to necessary conclusions. His natural philosophy likewise combined observation with reasoning about what observations meant. Science also involves a community of inquiry. One person might make initial observations or propose theories, but others must be able to check the work, test the claims, offer alternatives. Thales didn't work in isolation. He taught students who questioned his ideas and developed their own theories. This collaborative, critical approach became essential to science. No one person has all the answers. Progress comes through many people working on problems, correcting each other's mistakes, building on each other's successes. Thales also showed that science requires intellectual courage. He questioned beliefs that seemed obviously true and that everyone accepted. The earth looks flat and feels stationary. It takes courage to suggest otherwise. The gods seem to control nature. It takes courage to propose natural causes instead. Thales demonstrated the courage to follow reasoning and observation wherever they led, even when they contradicted common sense and traditional belief. Science also needs humility. Thales made claims about fundamental nature, but he didn't claim certainty. He proposed water as the basic substance, but this was a hypothesis open to questioning and testing. His student Anaximander proposed a different answer. This willingness to have one's ideas challenged and potentially overturned was crucial. Science progresses by discarding wrong ideas and refining better ones. Clinging to ideas regardless of evidence blocks progress. The practical orientation Thales brought to inquiry also characterizes science. He didn't just wonder about nature abstractly. He applied understanding to solve problems, measuring pyramids, predicting eclipses, improving navigation, managing river crossings. Science has always combined pure curiosity about how things work with practical concern for using knowledge to improve human life. Thales showed that these two motivations, understanding for its own sake and understanding for practical benefit, reinforce rather than conflict. Better understanding enables better applications. Practical challenges motivate investigation that yields theoretical insights. The merchant who needed to navigate safely and the thinker who wanted to understand celestial motions were the same person, pursuing the same knowledge for interconnected reasons. Science also requires a specific view of nature, that it's regular, orderly, intelligible, consistent. Thales embraced this view fully. Nature follows patterns. Similar causes produce similar effects. What's true here is true there. What happened yesterday will happen again tomorrow under the same conditions. Without these assumptions, investigation makes no sense. Thales didn't just assume them, he demonstrated them through successful predictions and practical applications. The explanatory goals of science also appear in Thales. He didn't just collect facts. He wanted to explain why things happen, to unify diverse phenomena under common principles. Why this diversity of substances? Because they're all water transformed. Why these celestial patterns? Because heavenly bodies move according to regular principles. Explanation meant showing how the unfamiliar reduces to the familiar, how the complex emerges from the simple, how the many are ultimately one. Thales also exemplified the scientific virtue of following evidence over authority. When observation conflicted with tradition, he trusted observation. When reasoning led to surprising conclusions, he accepted them. He didn't defer to priests or poets who claimed knowledge of nature. He looked for himself and thought for himself. This independence of mind became essential to science. The questions Thales asked became science's questions. What are things made of? Why do they behave as they do? What patterns govern events? How can we predict and control natural processes? These weren't new questions in an absolute sense. People had always wondered about such things. But Thales asked them in a new way, seeking natural answers based on observation and reasoning rather than mythological stories or religious revelation. Science also requires believing that knowledge is possible. If nature is too chaotic or too mysterious to understand, there's no point trying. Thales believed understanding was achievable, difficult, requiring careful work and clear thinking, but achievable. This optimism about human capacity to know nature drove his investigations and became science's driving force. Knowledge in most ancient societies belonged to priests. They controlled access to learning, deciding who could study and what they could know. Sacred texts and rituals remained secret, revealed only to initiates who proved themselves worthy. This priestly monopoly on knowledge gave religious authorities enormous power. If you wanted to understand the world, you had to go through them. Thales broke this monopoly. He taught in public spaces, in marketplaces and gymnasiums where anyone could listen. He didn't require initiation into mysteries or allegiance to particular gods. He didn't claim knowledge came from divine revelation that only special people could access. He said anyone willing to observe carefully and think clearly could understand nature. This democratization of knowledge was revolutionary. It suggested that understanding the world wasn't a matter of religious status or divine favor. It was a matter of using your mind. A merchant could understand geometry as well as a priest. A sailor could understand astronomy. A farmer could understand weather patterns. Knowledge belonged to everyone, not just a privileged class. The students who gathered around Thales in Miletus became known as the Milesian school. They included Anaximander and Anaximenes, who developed their own theories about nature. These students didn't simply accept what Thales taught. They questioned him, disagreed with him, proposed alternatives. Thales apparently encouraged this. He wanted students who thought for themselves, not followers who memorized his words. This critical approach to teaching differed fundamentally from religious instruction. Priests taught doctrines to be accepted on authority. Questioning sacred teachings was impiety. Thales taught methods of inquiry and encouraged questioning everything, including his own ideas. Truth mattered more than authority. If a student could show that Thales' theory was wrong, that was progress, not disrespect. This attitude created a tradition of philosophical schools, groups of thinkers working on shared problems but often disagreeing about solutions. The Milesian school was first, but many others followed. These schools weren't like temples where everyone worshipped the same way. They were communities of inquiry where debate and disagreement drove progress. Thales taught without charging fees, as far as we know. Some later philosophers made their living from teaching, but Thales supported himself through trade. This meant his teaching wasn't limited to wealthy students who could afford to pay. Anyone interested could join the discussions. This accessibility helped spread the new way of thinking beyond the elite who controlled traditional education. The content of what Thales taught also differed from traditional education. Priests taught mythology, ritual practices, techniques for divination and sacrifice. Thales taught geometry, astronomy, natural philosophy. He taught skills with practical applications like navigation and surveying, but also theoretical understanding for its own sake. Both practical and theoretical knowledge mattered. Thales also taught by example as much as by words. He demonstrated how to observe, how to question, how to reason from evidence to conclusions. Students learned methodology by watching Thales work through problems, propose explanations, test predictions. This apprenticeship model, learning by doing alongside a master, became standard in philosophical schools. The location of teaching mattered too. Temples were sacred space, set apart from ordinary life, controlled by priests. Marketplaces and gymnasiums were public space where citizens mixed and talked. Teaching in these locations signaled that philosophy belonged to ordinary civic life, not to a separate sacred realm. Anyone going about their daily business might stop and join a discussion. This public character of philosophy made it inherently political. When you discuss fundamental questions about nature and knowledge in public, you implicitly claim that such questions aren't the exclusive domain of traditional authorities. You suggest that citizens can think for themselves about important matters. This challenged not just priestly authority, but political authority too. If people can figure out how nature works without priests, maybe they can figure out how society should work without kings. The Greek city-states, especially democratic ones like Athens, provided environments where this kind of public intellectual life could flourish. Citizens were expected to participate in political deliberations, to speak in assemblies, to serve on juries. This required ability to think and argue clearly. Philosophy developed skills useful for citizenship, while also questioning traditional assumptions about society and values. Thales didn't just teach individuals. He created a tradition, a way of pursuing knowledge that continued after him. His students became teachers. Their students taught others. Ideas spread from Miletus to other cities. Within a few generations, philosophical schools existed throughout the Greek world. This self-sustaining tradition of inquiry became one of Greek civilization's most important achievements. The tradition also proved remarkably resilient. Political upheavals disrupted cities, wars destroyed property and killed people, but the tradition of philosophical inquiry survived. Teachers might die, schools might close, but as long as some people kept questioning and reasoning about nature, the tradition continued. Ideas can be destroyed, but as long as anyone remembers and values them, they can revive. Thales' teaching method emphasized understanding over memorization. He didn't want students to remember facts. He wanted them to grasp principles that would let them figure things out for themselves. A student who understood the principles of geometry could solve new geometric problems. A student who understood the method of looking for natural causes could explain phenomena Thales never discussed. This emphasis on understanding over memorization reflected Thales' view that knowledge is active, not passive. You don't acquire knowledge by receiving information and storing it. You acquire knowledge by engaging with problems, testing ideas, working through reasoning. The teacher's role is to guide this active process, not to pour information into passive receptacles. Thales also taught that knowledge builds on itself. Each generation doesn't start from nothing. Later thinkers stand on the shoulders of earlier ones, using their discoveries as foundations for going further. Anaximander could build on Thales' work precisely because Thales taught openly and left ideas for others to develop. This cumulative character of knowledge meant that open teaching accelerated progress. The questions Thales encouraged students to ask were open-ended. What is the fundamental nature of reality? Why do things change? How can we know anything with certainty? These questions had no final answers. Each proposed answer raised new questions. This open-endedness meant philosophy would never be finished, never reach a point where all questions were answered. There would always be more to investigate. This permanent incompleteness distinguished philosophy from religious doctrine. Religions claimed to possess final truth revealed by gods. Philosophy claimed only to be searching for truth through human effort. The search itself became valuable, not just finding answers. A good question that led to fruitful investigation mattered as much as any answer. Thales showed his students that disagreement could be productive. When Anaximander rejected water as the fundamental substance and proposed the boundless instead, this wasn't betrayal, it was progress. Anaximander had reasons for his view. Debating those reasons advanced understanding. Even if Anaximander was wrong, the arguments clarified what any theory of fundamental substance needed to explain. This embrace of disagreement created a culture of debate that characterized Greek intellectual life. Arguments weren't personal attacks. They were ways of testing ideas, exposing weaknesses, finding better alternatives. The goal wasn't to win debates, but to get closer to truth. If your opponent showed your idea was wrong, you thanked them for the correction and developed a better idea. The teaching tradition Thales started eventually produced the great philosophical schools of Athens: Plato's Academy, Aristotle's Lyceum, the Stoic and Epicurean schools. These institutions formalized what Thales began informally: communities of inquiry dedicated to understanding nature, humanity, and knowledge. They preserved and transmitted ideas across generations while also producing new insights. These schools educated people who became leaders in various fields. Students of philosophy became political leaders, military commanders, physicians, mathematicians, writers. The training in careful thinking and clear reasoning proved valuable in many domains. Thales started a tradition that shaped Greek culture and, through Greek influence, Western civilization. Thales never separated abstract thinking from practical application. His geometry helped builders and surveyors. His astronomy helped sailors navigate. His understanding of weather patterns helped farmers and merchants. Philosophy wasn't an ivory tower activity disconnected from ordinary life. It was a tool for living better and working more effectively. The story of measuring the pyramid's height exemplifies this integration. Egyptian priests knew the pyramid's dimensions, but they guarded this knowledge. Thales demonstrated that anyone with basic geometric understanding could measure the pyramid themselves. He made knowledge accessible while also solving a real problem. Travelers wanted to know how large the pyramids were. His method answered that question. Surveyors needed to measure land accurately to establish property boundaries and calculate taxes. Traditional methods worked but weren't precise. Thales' geometric techniques improved accuracy. Understanding that similar triangles have proportional sides let surveyors calculate distances they couldn't measure directly. They could find the width of a river without crossing it, or the height of a cliff without climbing it. These practical applications proved philosophy's value to people who might otherwise dismiss it as useless speculation. When philosophy helped you build a straighter wall or plant crops at the right time or navigate to a distant port safely, its value became obvious. This vindicated Thales' claim that understanding nature led to practical benefits. The olive press story made this point dramatically. Thales used his knowledge of weather patterns to predict an abundant harvest. This wasn't abstract theorizing, it was applying understanding to gain competitive advantage. The fact that a philosopher could outmaneuver ordinary merchants at their own game demonstrated that theoretical knowledge had real-world power. Whether the story is literally true matters less than what it reveals about how Greeks understood Thales. They saw him as someone who could move between theory and practice seamlessly. He could contemplate fundamental questions about reality and also corner the market in olive presses. Both activities involved the same capacities: observation, reasoning, anticipation, planning. Engineering projects required understanding of materials and forces. How much weight can a beam support? What shape should an arch have to carry a load? How deep must foundations go to support a building? These weren't just trial and error questions. They involved principles that could be understood through reasoning about geometry and physics. Thales' work in geometry laid groundwork for applying mathematics to engineering. Bridges needed to span rivers without collapsing. The story of Thales diverting a river to help merchants cross suggests he understood hydraulics and earth moving. Whether he actually did this specific project is uncertain, but the story captures the kind of problem-solving Thales engaged in. How do you make water go where you want it? Understanding water's nature, how it flows and where it flows, lets you control it. Navigation depended on understanding celestial patterns. Sailors needed to know which stars to follow at different times of year, how to judge their position by observing the sky when weather was likely to turn dangerous. Thales' astronomical knowledge directly helped sailors make voyages more safely and reliably. This saved lives and made commerce more profitable. The teaching of navigation techniques to Greek sailors shows Thales spreading practical knowledge widely. He didn't keep navigational secrets to himself or sell them at high prices. He taught openly, improving Greek sailing generally. This generosity with knowledge characterized his approach. Understanding belonged to everyone and served everyone better when widely shared. Calendar keeping required astronomical knowledge too. Farmers needed to know when seasons would change, when to plant and harvest. Religious festivals needed to be scheduled at appropriate times. Predicting solstices and equinoxes wasn't just interesting astronomy, it was practical knowledge that structured social and economic life. Thales' explanation of earthquakes, though wrong in specifics, shows him trying to understand destructive natural phenomena that affected people's lives. If you understood what caused earthquakes, you might predict them or at least understand where they were likely to occur. This could save lives and prevent property damage. Even a wrong theory was better than no theory if it prompted investigation and eventually led to better understanding. Water management was crucial in Mediterranean cities. How do you ensure adequate fresh water supply? How do you prevent flooding? How do you irrigate crops efficiently? Thales' focus on water as fundamental substance connected to these practical concerns. Understanding how water behaves, where it comes from, how it moves, had obvious applications. The geometry Thales taught wasn't abstract symbolism. It described real spatial relationships in the physical world. When you proved that the angles in a triangle sum to two right angles, you proved something about actual triangles drawn on actual surfaces. This meant geometric knowledge could be applied to architecture, engineering, art, anywhere people needed to work with shapes and spaces. Military applications existed too, though they're less documented. Building siege engines, calculating trajectories for projectiles, planning fortifications, all involved geometric and physical understanding. An army with better engineering and better calculations had advantages in warfare. Knowledge was power, quite literally, in both peaceful commerce and military conflict. Thales demonstrated that the person best able to understand nature abstractly was also the person best able to manipulate nature practically. The same understanding that explained why things happen let you make things happen. If you understood why water flows downhill, you could design irrigation systems. If you understood celestial motions, you could navigate and create calendars. Theory and practice weren't separate domains but aspects of the same enterprise. This unity of theory and practice became characteristic of Greek intellectual life. Philosophers weren't pure theorists disconnected from practical concerns. Mathematicians solved engineering problems. Astronomers advised sailors. Physicians studied human nature theoretically while also treating patients. Knowledge was meant to be useful, even when pursued for its own sake. The practical orientation also kept philosophy grounded. If your theory implied that something should work a certain way practically, but it didn't, that was evidence against your theory. The practical test provided feedback on theoretical ideas. This prevented philosophy from floating off into pure speculation, disconnected from reality. Thales' success in practical domains also gave him credibility when he made more abstract claims. If he could predict eclipses and measure pyramids and profit from olive harvests, maybe his ideas about water being fundamental substance deserved consideration too. Practical success suggested theoretical insight. The same mind that solved concrete problems might also grasp abstract truths. The tools Thales used were simple: measuring rods, basic astronomical observations, geometric diagrams drawn in sand or wax. He didn't have sophisticated instruments or laboratories, but he showed what could be accomplished with careful thought applied to basic observations. You didn't need elaborate equipment to make progress in understanding. You needed clear thinking and systematic observation. This accessibility meant that others could follow Thales' example without great resources. Anyone could observe shadows and practice geometry. Anyone could watch the stars and track patterns. The barriers to entry were low. This helped philosophy spread widely rather than remaining confined to wealthy elites who could afford expensive equipment or travel to study with distant teachers. One question changed the course of human thought. What is the basic nature of reality? Not how do things appear, but what are they really? Not what stories explain them, but what actually composes them. This question, simple to ask but profound in implications, launched philosophy and science. Before Thales, people wondered about things without asking this particular question. They asked who made things, who controlled them, what stories explained them. These questions assumed reality was ultimately about agency, about gods and spirits doing things. Thales' question assumed reality was about substance and properties, about what things are made of and how they behave. The shift from who to what represented a complete reorientation. It implied that understanding nature didn't require knowing intentions or hearing stories. It required analyzing composition and properties. This made nature a different kind of object for thought, something you could investigate through observation and reasoning rather than through myth and ritual. Thales answered that everything is water. This answer proved wrong, but asking the question was the real achievement. Once you ask what the fundamental nature of reality is, you can't stop investigating. Each answer raises new questions. If everything is water, why does water take so many different forms? What drives the transformations? How exactly do rocks and fire emerge from water? These follow-up questions pushed Thales' students to develop more sophisticated theories. Anaximander proposed the boundless, something indefinite from which definite things emerge. Anaximenes proposed air, which becomes denser or rarer to form different substances. Each answer opened new questions, driving investigation forward. The question assumed that diverse phenomena might have a common explanation. This assumption wasn't obvious. The world might be fundamentally pluralistic, with many different basic substances, each following its own principles. But Thales looked for unity, for a single explanation that could account for everything. This drive toward unified understanding became central to theoretical inquiry. Scientists still ask Thales' question. What is matter made of? Atoms. What are atoms made of? Protons, neutrons, electrons. What are those made of? Quarks and leptons. How far down does it go? Is there a final fundamental level, or does it continue indefinitely? These are Thales' questions in modern form. The question also raised methodological issues. How do you investigate fundamental reality? You can't see or touch whatever is most basic. Atoms and quarks are too small to observe directly. Water transforming into all other substances happens too slowly or at scales too small to witness. Yet you need evidence to support claims about fundamental reality. What counts as good evidence? Thales relied on what he could observe: water's transformations, its presence in living things, its cycles through nature. These observations suggested but didn't prove that water was fundamental. Later thinkers developed more sophisticated methods, but they faced the same challenge. How do you connect observable phenomena to claims about unobservable fundamentals? The question assumed that fundamental reality might differ from apparent reality. Things seem to be made of various substances: wood, metal, stone, flesh. Thales said this appearance is deceptive. Really, everything is water. This gap between appearance and reality became a central philosophical problem. If things aren't what they seem, how can we know what they really are? Different answers to Thales' question led to different worldviews. If everything is water, the world is fundamentally fluid and changing. If everything is atoms in void, the world is fundamentally discrete particles moving in empty space. If everything is energy fields, the world is fundamentally continuous vibration. Each answer shapes how you understand everything else. The question also connected to other philosophical problems. If everything reduces to one substance, what accounts for change? How does that one thing become many different things? Is change real or illusory? Is the fundamental substance eternal, or did it come into being? These metaphysical questions flowed from Thales' initial inquiry. Asking about fundamental nature also raised questions about knowledge. How can we know what's fundamental? Direct observation shows diversity, not unity. Reasoning suggests unity, but can reason be trusted when it contradicts observation? What's the relationship between sensory knowledge and rational knowledge? Thales opened epistemological questions that philosophers debated for centuries. The question assumed that reality has a nature to be discovered. It's not arbitrary or chaotic. There's something to know, some truth about what things are made of and how they work. This optimism about the intelligibility of nature made inquiry worthwhile. If reality was unknowable, asking about it would be pointless. Thales' question also implied that human beings can understand fundamental reality. We're not limited to knowing surface appearances. Through observation and reasoning, we can penetrate to deeper truths. This confidence in human cognitive capacity characterized Greek philosophy. We might not know everything, but we can know real truths about real nature. The answer Thales gave, everything is water, unified natural philosophy with cosmology and theology. If water is fundamental, then understanding water means understanding the cosmos. If everything is full of gods and everything is water, then water is divine. This created a unified vision where physics, metaphysics, and theology addressed the same reality from different angles. The question also had practical implications. If you know what things are fundamentally made of, you might be able to transform them deliberately. If everything is water, maybe you can turn lead into gold by understanding how to manipulate the underlying substance. This hope of controlling nature through understanding it motivated both ancient alchemy and modern chemistry. Different philosophers proposed different methods for answering Thales' question. Some relied primarily on observation, others on reasoning, still others on a combination. Some thought mathematics held the key, others focused on qualitative properties. These methodological debates shaped the development of science. The question assumed that explanation means reduction to something more basic. You explain complex phenomena by showing how they emerge from simpler elements. This reductionist approach became dominant in science. Explain biology through chemistry, chemistry through physics, physics through mathematics. Each level reduces to the next lower level. But Thales' question also opened space for anti-reductionist views. Maybe reality is irreducibly complex, with different levels that can't be reduced to each other. Maybe life can't be fully explained through chemistry or consciousness through neuroscience. The debate between reductionist and anti-reductionist views continues in philosophy of science. The question also connected to values and meaning. If everything reduces to water or atoms or whatever, what happens to qualities we care about? Beauty, goodness, justice, love, are these fundamental features of reality or just superficial appearances? Do they reduce to physical processes or represent something irreducible? Thales opened these questions about the relationship between fact and value. Thales died around 546 BCE, but his influence was just beginning. The students he taught carried his approach to new cities and taught their own students. Within a generation, philosophical schools existed throughout the Greek world. The conversation Thales started continued, growing richer and more sophisticated with each thinker who joined it. Anaximander studied with Thales in Miletus. He accepted the basic approach. Look for natural explanations, seek unity beneath diversity, use observation and reasoning, but rejected Thales' specific answer. Everything couldn't be water, Anaximander argued, because opposite qualities like hot and cold, wet and dry, couldn't all emerge from water. Water is already wet and cold. How could hot and dry fire come from something essentially opposed to it? Instead, Anaximander proposed that the fundamental substance must be undefined, having no particular qualities that would limit what could emerge from it. He called this substance the boundless or the indefinite. From this formless source, all definite things emerge through a process of separation, hot separated from cold, wet from dry, creating the diversity we observe. This represented progress through disagreement. Anaximander identified a real problem with Thales' theory and proposed a solution. His solution raised new questions. How exactly does separation work? What drives it? Why do definite things emerge from the indefinite? But these were better questions than before, more sophisticated, pushing toward deeper understanding. Anaximenes, another Milesian, proposed a third alternative. Everything is air, he said. Air becomes other substances through condensation and rarefaction. When air condenses, it becomes first wind, then cloud, then water, then earth, then stone. When it rarefies, it becomes fire. This provided a mechanism for transformation that Thales and Anaximander had left vague. All three Milesians agreed on the fundamental approach despite disagreeing about specifics. They all sought natural explanations. They all proposed material substances as fundamental reality. They all tried to explain diversity through transformation of unity. The shared framework mattered as much as their specific differences. The conversation spread beyond Miletus. In southern Italy, Pythagoras founded a school that emphasized mathematics. He taught that number is fundamental reality. Everything is ultimately mathematical relationships. This took Thales' geometric work in a new direction, making math itself rather than any physical substance the key to understanding nature. Heraclitus in Ephesus proposed that fire is fundamental and that everything flows in constant flux. You can't step in the same river twice, he said, because the river is always changing. This emphasized the dynamic aspect of reality that Thales' water theory had suggested, but Heraclitus made central. Parmenides in southern Italy went the opposite direction. He argued that change is impossible and illusory. Reality is one, eternal, unchanging. All apparent plurality and change is deception of the senses. Only reasoning reveals truth, and reasoning shows that what truly exists cannot change or divide. These diverse answers to Thales' question created productive debate. Heraclitus and Parmenides represented opposite poles. Everything changes versus nothing changes. Working through their arguments and trying to reconcile or choose between them drove philosophical progress. Each thinker sharpened their positions by arguing against rivals. Democritus proposed that reality consists of atoms, tiny indivisible particles moving through empty void. All apparent substances and qualities result from different arrangements of the same basic atoms. This answered Thales' question. What is everything made of? with a pluralistic rather than monistic answer. Not one substance, but many identical particles. Empedocles tried to mediate between monism and pluralism. He proposed 4 fundamental elements: earth, water, air, fire. All substances are mixtures of these 4 in different proportions. This preserved some unity, only 4 basic elements, while allowing more complexity than strict monism. Anaxagoras proposed that everything contains portions of everything else. There are infinitely many different substances, and each thing contains tiny amounts of all of them. What something is depends on which substance predominates. This radical pluralism represented another answer to Thales' question. Each of these thinkers built on what came before while also criticizing it. They didn't reject Thales' approach but refined and developed it. They asked better questions, proposed more sophisticated answers, used more rigorous arguments. This cumulative progress characterized Greek philosophy. The conversation also expanded beyond natural philosophy into ethics, politics, aesthetics, and logic. Socrates focused on moral questions. What is justice? What is virtue? How should we live? He used the same critical questioning method Thales applied to nature, but directed it at human concerns. Plato combined interests in nature, knowledge, ethics, and politics into a comprehensive philosophy. He proposed that reality has 2 levels: the changing physical world and an eternal realm of forms or ideas. This answered Thales' question, what is fundamental, by pointing beyond physical substance to abstract structures. Aristotle, Plato's student, brought philosophy back toward Thales' empiricism. He emphasized observation of nature and classification of phenomena. He developed formal logic, making explicit the rules of reasoning that earlier thinkers had used intuitively. He applied philosophical analysis to biology, physics, ethics, politics, and many other domains. Each of these major figures acknowledged debts to Thales and the Milesians. Aristotle wrote histories of philosophy that traced ideas back to their sources. He credited Thales as the founder, the first to ask the fundamental question about nature. This established Thales' reputation for all subsequent European thought. The conversation Thales started also spread beyond Greece. When Alexander the Great's conquest spread Greek culture across the Mediterranean and Middle East, Greek philosophy went with it. Islamic scholars preserved and commented on Greek philosophical texts during medieval times. European scholars later recovered these texts and built on them. The scientific revolution of the 16th and 17th centuries explicitly drew on Greek natural philosophy. When scientists like Galileo and Newton challenged medieval Aristotelianism, they often appealed back to earlier Greek thinkers like the Milesians. The emphasis on observation, mathematics, natural causes, and testable predictions came straight from Thales and his successors. Modern science answers Thales' question with extraordinary sophistication. We know matter consists of atoms, that atoms contain nuclei and electrons, that nuclei contain quarks bound by gluons, that all forces and particles are probably manifestations of quantum fields. But the question itself, what is fundamental reality, remains Thales' question. Philosophy departments in modern universities still teach Thales. Introductory courses begin with him, explaining how he initiated Western philosophy and science. Students read fragments from the Milesians and trace how later thinkers responded. Thales appears in the origin story philosophy tells about itself. This isn't just antiquarian interest in historical figures. Thales raised questions that remain live issues. What is the relationship between appearance and reality? How do unity and diversity relate? What methods yield reliable knowledge? Can everything be explained through physical causes, or does reality include irreducible mental or spiritual dimensions? Contemporary philosophers still debate these questions. The conversation format itself, the back and forth of proposal and criticism, theory and counter-theory, became philosophy's characteristic mode. Philosophers don't establish doctrines to be accepted on authority. They propose ideas to be examined, tested, argued about. The conversation never ends because there are always new objections to address, new implications to explore, new applications to develop. Thales also established that philosophical progress happens through disagreement. When Anaximander rejected Thales' water theory, that wasn't failure, it was success. Thales had raised a question important enough that people spent lifetimes trying to answer it better. He started a conversation that engaged the best minds for generations. This aspect of Thales' legacy might be his most important. He showed that intellectual progress comes through community inquiry, not individual revelation. No one person can answer all questions, but a tradition of people building on each other's work, correcting errors, refining insights, can make real progress over time. The conversation continues today. Scientists probe ever deeper levels of matter. Philosophers analyze consciousness and free will and meaning. The specific questions evolve, the methods become more sophisticated, but the fundamental inquiry Thales initiated persists. We're still trying to understand what things are really made of and how we can know it. 2,600 years separate us from Thales, yet his relevance persists. We live in a world transformed by science and technology, a world Thales couldn't have imagined. We know things he never dreamed of, use tools that would seem like magic to him, yet the fundamental approach he pioneered remains essential. We're drowning in information. Every day brings more data, more claims, more supposed facts than anyone can process. Social media spreads ideas instantly to billions. Anyone can publish anything. In this chaos, Thales' method matters more than ever. Don't accept claims on authority. Look for evidence. Think critically. Test ideas against observation. Modern life requires navigating between experts who disagree. Doctors disagree about treatments. Economists disagree about policies. Scientists disagree about environmental questions. How do you decide whom to trust? Thales suggests understand their reasoning, examine their evidence, check whether their predictions work. Don't just accept credentials, evaluate arguments. Technology has made us powerful but not necessarily wise. We can manipulate nature in ways Thales never imagined, but we don't always understand the consequences. Climate change, biodiversity loss, nuclear weapons, artificial intelligence, these challenges require both technical knowledge and wisdom about how to use it. Thales showed that understanding nature and thinking clearly about what to do with that understanding go together. Education today often separates specialized knowledge from general thinking skills. Experts in narrow fields may lack broad perspective. Thales exemplified integration. He was merchant, mathematician, astronomer, philosopher. He showed that the same mind can engage theoretical questions and practical problems, that understanding connects across domains. The scientific method Thales pioneered faces challenges from various directions. Some question whether objective truth exists at all. Others trust personal experience or religious revelation over systematic investigation. Still others cherry-pick scientific findings that support their preferences while rejecting inconvenient ones. Thales' example reminds us why the scientific approach matters. It works. It produces reliable knowledge that leads to successful predictions and useful applications. The question Thales asked, what is fundamental reality, remains relevant because it affects how we understand ourselves and our place in the universe. Are we just complex arrangements of particles following physical laws? Do we have free will? Is consciousness something beyond physical processes? How we answer shapes ethics, law, education, everything. Thales also showed the value of intellectual humility. He proposed answers but didn't claim certainty. He was wrong about many specifics, but right about the approach. In an age of overconfidence and polarization, when everyone is certain they're right and opponents are not just wrong but evil, Thales' example of holding strong views lightly while following evidence offers an alternative. The democratic character of Thales' philosophy matters now too. He taught publicly, made knowledge accessible, encouraged questioning authority. These values underlie modern democratic societies. Citizens in democracies need to think critically, evaluate evidence, make informed decisions. This requires the skills Thales taught: observation, reasoning, healthy skepticism. Environmental challenges demand understanding nature the way Thales did, as an interconnected system following regular principles. Climate science, ecology, geology all build on the foundation Thales laid. Understanding how nature works gives us hope of addressing environmental damage before it becomes catastrophic. Technology today feels magical, but it isn't. It's applied understanding of nature. Every device, every algorithm, every medicine rests on knowledge gained through the methods Thales pioneered. When we forget this, when we treat technology as magic or accept it uncritically, we lose our ability to control and direct it wisely. Thales' integration of theory and practice offers a model for education. Schools sometimes teach facts divorced from application or skills divorced from understanding. Thales showed these belong together. Understanding why things work makes you better at making them work. Practical challenges motivate theoretical investigation. The conversation Thales started continues in every lab, every classroom, every public debate about science and policy. We're still arguing about fundamental questions. What is real? How can we know? What should we do with knowledge? The specific content has changed, but the basic questions persist. Thales showed that progress comes through community inquiry over time, not individual genius solving everything at once. This matters in an age that often celebrates individual brilliance while ignoring collaborative effort. Science works because many people contribute, building on each other's work, correcting each other's errors. No lone genius produces all knowledge. The courage to question that Thales demonstrated remains necessary. Every society has sacred cows, assumptions everyone accepts without examination. Progress requires people willing to ask uncomfortable questions, to challenge conventional wisdom, to follow reasoning wherever it leads. This takes courage because it invites criticism and ridicule. Thales' naturalism, his insistence on natural explanations rather than supernatural ones, matters in ongoing debates about science and religion. You can hold religious beliefs while also accepting that natural phenomena have natural causes. Thales himself said everything is full of gods while also explaining everything through water and physical processes. The two aren't necessarily incompatible. The unfinished character of inquiry that Thales established remains true. We know vastly more than ancient Greeks, but we're no closer to final answers. Each discovery raises new questions. The universe keeps surprising us. This means the work Thales started will never be finished. There will always be more to investigate, understand, explain. Thales matters because the habits of mind he cultivated remain essential. Question assumptions, seek evidence, look for patterns, think clearly, test ideas, accept uncertainty, value truth over comfort. These intellectual virtues don't come naturally. They must be taught and practiced. Thales showed how. The optimism Thales displayed about human capacity to understand nature offers hope. We face enormous challenges: environmental, technological, social, political. Understanding won't solve everything, but it gives us a chance. If we follow Thales' example, observe carefully, think clearly, work together, we can make progress. In an age of specialization, Thales reminds us that broad thinking matters. Connecting different domains of knowledge, seeing relationships between apparently separate questions, approaching problems from multiple angles. These skills come from refusing to be narrowly specialized. Thales, the merchant, mathematician, astronomer, philosopher, shows integration is possible. The legacy Thales left isn't just historical. It's active in every scientific investigation, every philosophical discussion, every critical examination of claims and evidence. When anyone anywhere looks at the world and asks why, when they seek natural explanations and test them against evidence, they participate in the tradition Thales founded. 26 centuries after his death, Thales lives in the questions we ask and the methods we use to answer them. His specific theories failed, but his approach succeeded beyond anything he could have imagined. This is his true legacy. Not answers, but questions. Not doctrines, but methods. Not finished knowledge, but ongoing inquiry. The conversation he started continues. The questions he raised remain vital. The habits of mind he exemplified remain essential. In this sense, Thales is not dead and gone, but alive in every careful thinker, every curious observer, every person who refuses easy answers and demands evidence and reasoning. The merchant from Miletus who looked at the world and asked why changed human thought forever. His gift to us is the conviction that we can understand nature, that observation and reasoning reveal truth, that knowledge is possible and valuable and worth pursuing. In a world that sometimes seems to reject these ideas, Thales' example reminds us why they matter and how much we lose if we abandon them.